For the final part here, what I want to do is look at a single example that is a difficult one that puts all of these ideas together: stoichiometry, system versus surroundings, and calorimetry, and then just Q equals MC delta T. So the example is, how much ammonium nitrate must be used in a cold pack containing 250 milliliters of water to lower the temperature of the water from 25 degrees Celsius to 5 degrees Celsius. The density of water is 1 gram per milliliter. And here is the chemistry that you're using to to lower the water using ammonium nitrate. So that's NH4NO3. So there are some slides where annotated slides walking through kind of the process, but I'm not going to talk through those. Instead, we're going to talk again about the idea that you can kind of set up a picture as to what's going on here. These enthalpy problems this is a real life example. You're designing a cold pack. It's 250 milliliters of water. You want it to be an instant cold pack. So you kind of start a process, chemical process, and you want to lower the temperature to 5 degrees. 25 degrees Celsius is pretty close to room temperature. So you want to set it up that you're going to lower this temperature of water. And what you're going to do is you're going to use ammonium nitrate. This is what is really used. In an instant cold pack, you basically just have a little sealed pack of this ammonium nitrate powder. When you break open the ice pack, what you're doing is breaking that seal, and then it just allows it to dissolve in the water, right? It just dissolves in the water. That dissolving then has an associated heat, and that can cause the water to cool down. And so what we want to know is how much ammonium nitrate do we want to add in? This is just an engineering problem. This is a design problem that we can now do. You know enough about everything having to do with thermodynamics to figure this out. And so we can I'm going to talk through that, but we can also think about some of the ideas of, now we can also kind of know enough, is this even a good chemical process to use, right? The idea is we want to make the water colder. Is this going to work? And so what we can really key in on is the fact that this is an endothermic process. Dissolving ammonium nitrate into water is endothermic. We can tell that because the delta H is positive. So the energy is going to go into causing this process to happen, dissolving the ammonium nitrate, which means it has to come from somewhere, and it's going to come from the water. So when you want to do these processes, we can kind of qualitatively even check. I told you were going to use ammonium nitrate, but now you can also figure out what sort of chemistry is appropriate for an instant cold pack. Instant hot packs, you just use a different solid that when it dissolves is exothermic, right? You don't want to do anything crazy. You don't want to do like a chemical reaction, anything that's super reactive. You just use dissolving. And so dissolving, there are solids that when they dissolve, it's exothermic, so they make the water hotter. In this case, when ammonium nitrate dissolves, it makes the water colder. So you just pick whatever you want, and that's how you can kind of design these things. So qualitatively, you know that an endothermic process is going to be the best, what you need to make this happen. So that's kind of the broad overview. And again, when you're working these kind of problems, you can draw out pictures. You can really kind of conceptualize these ideas in that way. So let's actually work through it now on some paper. Let's see how it goes. Okay, so we want to know an amount of ammonium nitrate. We are in a situation where we're working to, this is a kind of a real life product design. We want to make a cold pack, and we want that cold pack to have 250 milliliters of water. It's going to use ammonium nitrate dissolving into that water as the chemistry to cool it off. And we want to know how much ammonium nitrate are we going to need to add in order for this amount of water to go from 25 degrees Celsius to 5 degrees Celsius when we activate it. This is like an instant cold pack. This is the kind of product design we want to be able to do, and really kind of the chemical analysis of how heat is going to be involved in this kind of situation. So the end goal is how much ammonium nitrate. And whenever we see that how much ammonium nitrate, that is a mass of ammonium nitrate. All of these specifications have to do with water. The only place where ammonium nitrate comes up is in this chemical equation. And there's a delta H with it. When we see how much ammonium nitrate, that's a mass of ammonium nitrate. We're trying to do a stoichiometry problem, right? This is the end goal. The last step is going to be stoichiometry. So the question is, what would we plug in? Well, it's not like we don't care how much ammonium or nitrate is dissolved. What we care about is the heat associated with it. So we've seen previously you can go from amounts of reactant or product into the heat, but we're going to go the opposite direction. So that's going to be our last step, using this to convert between a desired amount of heat and an amount of reactant. So how much heat do we need then? And it's going to be based around cooling off our water, we can see. And so, we can think about, all right, well, I want to know, I'm going to cool off the water. So the question is basically, how much heat do I need to pull out of this water? Okay. And we know we're going to use our original equation for cooling off the water. So M water, C of water times delta T of the water. Well, am I given the mass of the water? No, but I am given a volume of water and I'm given a density. And so 250 milliliters of water. I know that it is 1 gram of water for every 1 milliliter of water, which means 250 grams of water. Hey, look, chapter 1, still coming back. Okay, so we can plug that in. 250 grams of water. What about my specific heat capacity of water, my little c? Am I given specific heat? No, but the important thing is I can always look it up because I know I'm dealing with water. Okay? So this is going to be 4.184 joules per gram degree Celsius. Temperature of the water is going to be final temperature of the water minus initial temperature of the water. So 5 degrees Celsius minus 25 degrees Celsius. If I put all of that together, I get negative 20,900 joules. So that's a lot. I'm going to convert that into negative 20.9 kilojoules. Dividing by 1,000 to go from joules into kilojoules. So one thing we can do right here is we can kind of check ourselves. This is going to be a long problem. We want to check ourselves along the way. I have gotten a negative number for my heat. I want to think about, does that make sense? Does it make sense that what that means? Well, a negative heat implies that heat is coming out of that object. Heat is coming out of the water, which is consistent with making a cold pack. I am trying to cool off my water. One of the most common mistakes that would be made is you would swap the 5 and the 25, right? This is negative 20, but instead you put a positive 20 into the calculation and get a positive number here. But heat is not going into the water because it's a cold pack. So heat is going to be leaving the water is what we would expect. So heat's leaving the water. Where is it going? Well, it's going into this reaction or this dissolvent. And we know that that is negative heat of the water. So negative of a negative, that's positive 20.9 kilojoules. So our target for how much heat to pull out of the water is really kind of the product specification, what we need, what we want our cold pack to accomplish. And so that tells us how much heat needs to come out of the water, which means we need to design this process. We need to set this process up to take out that much water. Okay? And so what that would mean is then we need 20.9 kilojoules. That's how much we need to come out of the reaction. And we can see that our conversion factor is going to be this right here, the 28 kilojoules per mole. So we know that that means that it's 28 kilojoules for every 1 mole of my reactant right here. All right, I can use this. Let's bring it down right there. And so we can see that this is similar to stoichiometry. That really the purpose of doing this reaction here is to affect heat. It's to pull in the heat because this is an endothermic process. And so we have a target amount of heat we want to pull in. That's a target cause or effect of the reaction. So the question is, how much reactant do I use? I've gone from heat into amount of reactant, turn it into mass to get that final answer, useful answer. Calculate the molar mass of ammonium nitrate. It is 80.04 grams. And so collectively, I need 60 grams of ammonium nitrate. And so we can see that we can put together everything we want. You know, we want to make a cold pack. What kind of reaction should we use? It should be endothermic. Okay, well, then, you know, if we have our target for a certain, you know, we need a certain amount of heat pulled out of the water, well, we can know not only do we need to use an endothermic reaction, but based on the enthalpy, we can figure out exactly how much of that reactant we need. And so 60 grams of ammonium nitrate with your 250 grams of water, if that all dissolves in there, your water will go from 25 degrees Celsius, about room temperature, down to 5 degrees Celsius, which is quite cold. And so, you know, that would give you the cold pack effect that you are looking for. And so, you know, the stuff, this insight that we've talked about so far, what we've covered so far, you can see really does have a lot of applications in kind of how we think about heat flowing and heat moving around in chemical systems. And we can really do real life applications of this kind of actual, you know, engineering that would really go into designing one of these sorts of products that's based around using a process involving chemicals to change the temperature of what's going on around it. You know, a lot of times we heat things up using chemical processes, but we also can cool them down.
Now it's time for you to get some practice, seeing if we can put it all together. This is a hard one. Want to see what you can do. Again, you're not necessarily not going to grade you on it getting perfectly correct. Just want to see how you can work through this difficult problem, kind of putting all the parts of chapter 5 that we've talked about so far, putting them all together. So question 3 for participation 3.5. Suppose 5.75 kilograms of ethanol is heated by burning 35.2 grams of CH4 according to the reaction below. How much does the temperature of ethanol increase? So what is the increase in the temperature of the ethanol? The specific heat capacity of ethanol is 2.46 joules per gram degree Celsius. The reaction I'm looking at for the combustion of methane is CH4 plus 2O2 becomes CO2 and 2H2O. I forgot to put gas, but these are all gas. They're all gases in there. And the delta H for that reaction is negative 882 kilojoules per mole. So this is question 3 for participation 3.5, due Friday, March 5th at 11:55 p.m. on Blackboard. Suppose 5.75 kilograms of ethanol is heated by burning 35.2 grams of CH4 according to the reaction below. Arrows pointing to it. How much does the temperature of ethanol increase by? The specific heat capacity of ethanol is 2.46 joules per gram degrees Celsius. All right. There were 3 questions for participation 3.5 that you want to be on the lookout for. I want to make sure you find all 3 of those, get them answered, get that submitted by Friday, March 5th. If it's still Thursday, make sure you take a look at that midweek 8 homework over on Sapling. It's about the first set of videos. Otherwise, you're looking to the week 8 homework due Saturday, covers everything from this week, all this enthalpy, stoichiometry ideas. And then the heat effects lab puts it all together due Sunday at 11:55 p.m. Make sure you take a look at all this before you check out for spring break. There will be a answers video for participation 3.5 that becomes available Friday night. Otherwise, that's it for any sort of week 8 content. We'll have spring break next week. Week 9 will follow that, where we'll finish chapter 5 and have test 2. So if you have any questions about any of that kind of stuff, the review for test 2 will be available before spring break, so you can take a look at it all. Otherwise, have a great weekend. Enjoy your spring break, and I'll see you the following week, ready to finish the second half of the semester. Bye-bye.